All right, so I believe we are live on YouTube. I'm also going to see if the website can show some simulations that you can try. Let's see. Okay, so I think we'll just get started with a local version of some of these simulations of these card tricks. I think they're probably best done with the actual physical pack of cards, but I don't have. Maybe I'll fix this in the coming meetings, but I don't have a setup where I can nicely show you what's going on my table. So right now we are going to instead just stare at a screen and look at how hammer shuffles work. That's the theme for today. So let me stop sharing the coming soon screen and let's move on instead to actually checking out some simulations. So okay. Sorry, this is taking a minute, but it should be here anytime. Okay, so hopefully now you can see on my screen a page which says Royal Hammer. Can you give me a +1 in the chat if that's what you're currently seeing? Okay, awesome. All right. So this is the very first trick in the book. It only requires a set of 4 cards, and I'm actually holding up. I could actually show you on camera, but it's not going to be very helpful. But I encourage you to pick up a collection of 4 cards. Okay. It's probably simplest if they're like 1, 2, 3, 4 or something, but they don't have to be. Can be any 4 cards. And here's what we are going to do with these 4 cards. There's basically 3 phases to this performance or this trick. First, we are just going to stack the cards up like a very small deck. All of them are face down, and we want to make a note of the card that is at the bottom. So I'm going to actually show it to you here. Okay, so we can take a peek at the bottom card, which in this case happens to be the 6 of spades. And remember, you have yeah, the stack is not drawn vertically here. The card that's leftmost is the top, and the card that's rightmost is the bottom, as is labeled here. Okay, and we've taken a note of the bottom card. In fact, I keep forgetting, so I've actually written it out here explicitly. So the bottom card is 6 of spades. And in the first step, what we are going to do is we are going to move the top card to the bottom and flip over the card that then emerges in the top. So the card that in the original deck was the second card is going to now be flipped over. So I really encourage you to follow along with your own set of 4 cards. So this is very simple. We just push the top card to the bottom and flip over the card that's on the top. And then we can do this so-called cut and flip operation, which you may already be familiar with as a sort of a standard atomic operation with card tricks. It's called CATO, CATO, so cut and turn over. So what we're going to basically do is we're going to pull out any number of cards from the top of the stack. This is really small stack. So basically you can either pull out nothing or one or two or three cards and basically push them to the bottom of the stack. And then you're going to take the top two cards together and flip them over. Okay, so this is a single cut and flip operation. You can do this as many times as you like. Here on this page, I can choose how many cards I want to cut. It's randomly selected for me by default. So here I'm going to cut three cards and flip over the top two. So this is what's going to happen. So remember, when you're flipping the top two, what's happening is that their face up, face down change, their face up, face down state is getting toggled, and their positions are also getting swapped. Okay, so if you're doing the physical version, you can probably see that happening. Um, and okay, so Ritu is asking, is the cut and flip the same as standard shuffling while playing? So I guess there are many kinds of shuffles that people do. So, for example, there is the riffle shuffle where you split the deck out into two parts and then interleave them. The cut shuffle is probably like the simplest kind of shuffle where you're just uh, taking a bunch of cards off the top and pushing it to the bottom. So that's a cut shuffle. The flipping, I think, is not it's not a standard portion of most shuffles that I know of. But it is kind of special to this particular. So this particular shuffle, as we will see, is called the hammer shuffle, and it involves repeated applications of cutting and flipping cards over. So it is a specific shuffle. I'm not like I don't know enough, I think, about cards in general to know if it's standard. But the usual things that I'm aware of that people do is they either do riffles or they do like a very quick sequence of cuts. Those are fairly common. I don't know if the flipping is a particularly common part. So like Julian is saying, maybe it's like a restricted, like a special case sort of a thing. So the thing is, you can do this cut and flip business like as many times as you like. I'm cutting two cards every time. I could do fewer. This time I do one, etc. So this goes on for a bit. You could completely skip this step as well, but it's usually more impressive if you do it like a random number of times because it really feels like something totally random is happening to this deck. But as it turns out, what will happen once we are happy with the amount of cutting and flipping that we have done is when we go to the final step, the bottom card that we made a note of is going to sort of reveal itself, no matter how many times you did this cut and flip business. So to make the bottom card sort of pop out of the deck, here's what we are going to do in the final phase. And this we are going to do only once. So if you're following along, then this involves like three steps, which you want to do carefully. So what we're going to do is take the top card, flip it over and push it to the bottom. Take the next card and just push it to the bottom without flipping. And then we are going to flip the top card. That's the final phase of this trick. So we are going to finalize this. Take the top card, flip it over, push it to the bottom. Take the second card and push it as it is, and then flip over the top card. And as you can see here, the only card that is face up is the six of spades. Yeah. So what's going to happen for anybody who is following along is that the bottom card of your deck is going to be the only card that is facing a particular way, and all the other cards face the other way. So if you do all of these operations and kind of spread the cards out on the table, what's going to happen is either all the other three cards, not the bottom card, are face down and the bottom card is face up, or it's going to be the other way where the bottom card is face down and all the other three cards are face up. So we can do this a couple of more times. So here it's a fresh deck. So we have the 10 of spades at the bottom. We're going to initialize this. I'm going to do a couple of cuts and flips. And then let's finalize. And here, once again, the 10 of diamonds, which was the bottom card, shows up face up and at the bottom position. That's a coincidence. So that's what happened both times. That's not necessarily how it's going to go. It can show up anywhere, and it can also show up facing the other way. However, every single time, um, it's going to be the only card that's facing a certain way. So here, two of spades was the card at the bottom, and you can see that now it shows up at the top of the deck, and it's face down while all the other cards are face up. So there's a little OCD about this. So I added this toggle functionality so that I could just flip everything over, which you can also do when you're doing it physically if you like. Okay. All right, so give me like a +1 in the chat if the steps made sense and if this worked for you, if you tried it out and if it worked for you with your deck. Oh, very awesome. Okay, all right, super cool. And of course, like the typical question that we want to ask after seeing something like this is why does it work and like how was the setup? And I think that's actually a nice thing to puzzle over. I don't think, unless you've already seen this before or something like this before, I don't think it's entirely obvious why it works. So it's a nice thing to puzzle out, and I don't plan to spoil this entirely in today's discussion because according to our plan, which I think I want to maybe go back to for a second, I didn't do any like introductory comments about what we are going to do. So I'm just going to say that for today and tomorrow, we are going to be looking at the first chapter, which is about hammer shuffles and what you can do with them. And so for today, we are going to look at properties that are preserved by this, uh, cut arbitrarily and flip over the top two. That's what we're going to be looking at. And the thing that we want to think about ahead of the next discussion is how do these properties actually power up this trick? What's the connection? And we also want to see if we can sort of design our own tricks based on our understanding of properties of the hammer shuffle. Okay, so hopefully that sounds like a plan. Let's go ahead and okay, so if there are any questions, this would be a good time to just give ourselves a pause and ask. Again, let me know if, just in case this didn't work for you for some reason, or if the steps were not completely clear, like let me know. But essentially, we have like this, the initial phase sets up the trick for the final reveal. What we're doing in the middle is this kind of hammer style shuffle, which you can do for as long as you want. And then the final phase is kind of resetting things to some sort of a predictable state. So it's important to like, if you, okay, from a performative point of view, I think it's kind of important to remember what's going on in the initial and the final stages because um, for example, if I sometimes end up forgetting to flip the top card or something like that. And so there are these basically 5 steps in the initial and final phases combined. And those have to definitely be executed with precision to guarantee this outcome. So that is something that you do have to commit to memory if you're performing. The hammer shuffle part of it is easy, and because you kind of get used to doing this cut and flip over, that's something that just becomes very natural to do. But the first and the third steps are kind of critical to guarantee the outcome that you want. Okay. So, all right. So I'm going to pause and stop talking for like 10 seconds to see if there are any questions about like this particular 4 card trick.
So you cut first and then flip, or you flip first and then cut. What was it?
Actually, it turns out that it doesn't matter.
Oh,
But
I see. Okay.
yeah, but you could, you could, I think, do it either way.
Okay. Okay.
Yeah. And I think we'll try and see why in a minute. But in this, I think just to be faithful to, I think the presentation in the book, I think that they encourage you to flip first and then cut, I think. So I've probably not written it in a very consistent way. The operation is, I think, abbreviated CATO. I think it's kind of coincidental that when you pronounce that, it sounds like the Hindi word kato. So that's I found that amusing. But CATO is cut and turnover. So cut first and turnover. But I think it actually is sort of, in a certain sense, it's commutative. It doesn't matter which way you do it. So it's a good question, and we're going to come back to that in just a minute. So Vinod's asking if this is specific to 4 cards or any number of cards. So there are certain, again, very good question. So I think this particular thing about revealing the bottom card, is actually like kind of really specific to working with four. But there are other effects that you can like that are slightly more impressive that you can do with a larger number of cards. And I think if you wanted to do specifically reveal the bottom card with, let's say, 6 cards or 10 cards or something like that, you'd have to think about how to adapt the initial and final phases. It's in principle possible, I think. But it probably will involve like a more complex sequence of moves to actually make it happen. So what's more common for people to do with, and in fact, one of the tricks described in the book is this thing where they work with 10 cards and they set things up, they set up these moves so that after you're done with everything and you sort of lay the cards out, what comes face up is like this. What is this called? A royal flush, the thing where in poker the top cards of a particular suit. So you see the ace and the the face cards and so on. So basically, if you have a special set of cards, the other thing that it's a little cheesy, but if it's like you're performing on Valentine's Day or something, you can take a random set of 10 cards, which have 5 hearts and like 5 cards, which are not heart cards, but some other suits. And then you can do these hammer shuffle operations. So you do them carefully enough. When at the end you lay it out, all the hearts will be face up. They may not be consecutive or they may not be alternating or anything, but all the hearts will be face up and all the other cards will be face down. So it's like basically with the hammer shuffle you can get any subset of cards that you want to sort of emerge if you plan appropriately. So with 4 cards it's easy to get just the bottom card to emerge. If you want only the bottom card to emerge with a larger deck, I think you'll have to basically it's a good exercise to think about. It's definitely like I think possible to rig it, but we'll have to figure out what the operations should be. But it's interesting to think about. Like one of the things I wanted to stop with is to think about like how do you get, like let's say you have five cards that are special and you want only those to be face up at the end of your performance. How do you set that up? And there's also like a reason why we're always working with an even number of cards because it turns out to be convenient. But I think there have been extensions, and in fact I think there are comments in the book about how you can also make it work with an odd number of cards, like especially in tricks where you're just pulling a random, like somebody hands you a deck and you just pull out a random set of cards to work with, and it's not an even number. You don't want to be stuck. So there are ways of I think adapting to emergencies like that. But actually I haven't looked at the details of how you pull that off. So we will probably look at that in a bit. Um, Okay, are there any other questions or comments? Okay, all right, great. So okay, so now we have like these 10 cards, and this is like, I think, the first lemma-ish thing in the book. So here's the claim. The claim is that if you start with all your cards face up, right? Now, if you think of like these cards laid out, like a pattern is a permutation of the cards along with a state, which is for every card, it's either face up or face down. So I suppose the total number of possible patterns that you can have would be something like n factorial for the permutations multiplied by 2 to the n. For each of those permutations, you can also have like a bit string which tells you which card is face up and which card is face down. So that's 2 to the n possible states for which cards are up and which are down. Okay, so these are this is a space of all possible patterns. Now we're going to start with like, just the identity permutation and all cards are face up. And now what we are trying to track is the number of face-up cards at odd positions and the number of face-up cards at even positions. In the beginning, I have 10 cards and they're all face-up. So that's clearly 5 and 5 cards that are face-up at odd and face-up at even positions. Now what we're going to do is we're going to do like a random number of cuts and flips. Uh, and you're probably trying to track how many face-up cards at odd and how many face-up cards at even positions. So maybe just to make this like maybe a little more interactive, I can cut and flip at numbers that come in at the chat. So does somebody want to break this? Like we see that the number of face-up cards at odd positions and even positions always equal. Is there some way that we can make them different, or do you believe that that's sort of an invariant that will remain? So okay, I see 7, so I'm going to do 7 followed by 9. Okay. I see a 2. I see a 4. All right. Any more suggestions for where you want to cut? Okay, we do a 1. Okay, 2. All right, so let's try 2. So it really feels like at least the empirical evidence so far seems to suggest that the number of face-up cards at odd and even positions are exactly the same, no matter where we cut this deck. And that seems kind of suggestive. But by just looking at what's going on, um, would somebody want to maybe make a conjecture about this being an invariant and attempt thinking about why that's actually true? Okay, so Deepika is saying because 2 are face up every time. Actually, I guess you could cut it in a way that if you're thinking about the top 2 cards, okay, I think I've kind of, yeah, I mean, in these examples, it does seem like, yes, it doesn't have to be true in general. So, for example, uh, here, the top 2 cards are not like, they're not both face up. I don't know if that's what you meant. But the top 2 cards could have any pattern of face up, face down. Okay, what if we do a number twice or more? Do you mean like cut the same amount every time? You could do a sequence of, like for example, let's just cut one card multiple times. And if you kind of observe what's going on, you'll see that it's still the same. They really seem like these numbers cannot be made to be made different. Um, yeah, so as we can see at the top, you can have a face up, face down, or a face down, face up combination. Um, but okay, so Mohit is saying since the top 2 cards are flipped after every cut, one odd and one even position only is updated. Actually, it is useful, I think, to think of the flip and the cut separately. Uh, this comes back to the point about how it doesn't matter if you flip first or whether you cut first. So let's maybe focus on the flips first, because what's going on with the flips is that when you just flip the top 2 cards, what's going to happen is if they look different, they're going to continue to look different in the same way. So if you have a physical deck of cards, just try doing the top 2 cards in all possible positions. So if they're both face down and you flip them both over, then you get 2 face up cards, which means both the odd and the even side gain a face up card. If they both face up and you flip them over, they both become face down, which means that both odd and even positions lose a face up card. And if it's like here, if it's face up and face, sorry, this is face down and face up. If it's face down and face up, when you turn around and flip these over, what's going to happen is 2 is going to come in 6's place and it's going to become face down, and 6 is going to go to 2's place and it's going to become face up. So from the point of view of the face up, face down pattern, actually nothing changes as far as odd and even. So the card itself has changed, but so again, at the top of your deck, if you have one card face up and one card face down and try to flip it over, you'll find that the face up and face down configuration is exactly the same as before. So and the first position is an odd position, the second position is an even position. So when the cards are facing different ways, when you flip them over, actually literally nothing changes as far as the number of face up and face down cards are concerned. Whereas if they're both facing the same way, then either both odd and even positions lose or both odd and even positions gain a face up card. Okay, so if they were equal to begin with, then because the gains and the losses are also the same, they remain equal. Okay, so the flips maintain this invariant if it was true to begin with. Now, what about the cuts, right? So you could cut at an even position or you could cut at an odd position. So again, it's easier if you're experimenting with it with an actual like set of 10 cards in your hand or whatever number of cards you're comfortable with. But notice that when you're cutting, what you're doing is either all cards that were in even positions before remain in even positions, and all cards that were in odd positions before remain in odd positions, or the other way around. They get nudged up a bit. So for example, if I were to only cut the top here, so this card, which is 6, which is face down, was at an even position, and it moves. Right. So this moves. Let's see. This moves all the way to the end. Okay, these guys get flipped over. But basically, my point is that the cuts either swap the set of odd and even cards or keep them the same. So in any case, if the numbers of face up cards and face down cards were the same before, they continue to be the same now. Does that sort of make sense about the flips and the cuts being um, face number of face up cards equal to, okay, in odd and even positions being equal, like that property being preserved? Does that make sense across flips and cuts? So I see like a couple of thumbs ups, which is helpful. Let me know in the chat if this was like confusing or if this makes sense. Like if you actually play around with the cards, I think you get like a feel for it, but it's also hopefully mathematically clear. Okay, so if you prefer to be like a little more formal about it, I guess you could wrap this around in like some sort of an induction argument, saying, well, it's true in the beginning, certainly, and let's suppose that it's true after k steps. And so you have the property that it's an arbitrary configuration, but we assume by the induction hypothesis that the number of face-up cards in even and odd positions is the same. And then and then you kind of um, argue that, well, let's look at the flips and the cuts separately and see what happens to their states when you move things around. Okay, so okay, I'm just going to play around a little bit with a few other cuts and see if actually what I should have done is probably labeled these positions so that was a little easier to see what's moving where. But I think the before and after would have been perhaps a little confusing. So I'm actually think I think I should probably be a little more careful about the argument that I'm making with the cuts because Okay, I mean, if you think of it as some sort of a circular arrangement, I think it's a little clearer that what I said probably happens. But here, I think somebody's also pointing this out in the chat. When I just cut one, what I said is probably not entirely true in the sense that, okay, we have to ignore the flips for now. But okay, so if you ignore the part, okay, so when you cut the deck, right? So the bottom and minus k cards like move a distance of k, right? So let's say we're just cutting one card. So all of the other like 9 cards experience like a single left shift, okay? Which means that like somebody at position 2 comes to position 1, somebody at 3 comes to 2, somebody at 4 comes to 3, and so on. So all of these guys experience change of parity. Does that make sense? Like for that part of the cut? Yeah. So all the odds become even, and all okay. So the first card in the first spot now moves to the 10th spot, which is again now a shift in parity because the first position is an odd position, and the last position is an even position. So I think if this was like imagine this being arranged on like a circle that you can sort of toggle in some sense, and if the distance that is being traveled is like an odd amount of distance, then everybody's parity switches. But if the distance being traveled is an even amount, then everybody's parity remains the same. So if you chop off the top 2 cards, for example, then what was in the 3rd position comes to the 1st position, what was in the 4th position comes to the 2nd position, and so on. So the parity is retained. And so whoever was an even card before is still an even card now, and whoever was an odd card before is an odd card now. And you can argue that that's the same for the 2 cards that went to the bottom of the deck as well. Okay, so either these sets of odd and even cards stay exactly the same, or they're just swapped. So nothing really changes as far as the number of face-up cards in both batches go. Right, so Sunita is asking if this invariant would hold even if the number of cards are flipped, by which we mean um, Um, okay, so I'm not sure what it means for the number of cards to be flipped. I mean that in the initial state they all like in the initial state, I guess they can, as long as you start off with the invariant being true, this would carry forward. But maybe you mean something different when you say the number of cards are flipped. Oh, I see, I see. Okay, so how many do you chop off from the top? Yes, yes, that's a good point. So actually, the hammer shuffle is more general than turning over 2 cards. You can turn over. Um, I should be careful. I think you can turn over any even number of cards, and I think that should work for I think the same reason. Like it certainly would not work with flipping 1 card because that changes things. But I think Sunita is saying if any even number of cards were flipped, it would still work. That's absolutely right. Okay, how many cards can be flipped at once? Actually, that's kind of up to you. As long as you flip an even number of cards, this would work. So as far as this property is concerned. And in some sense, this property is like basically lies at the heart of what drives a lot of the hammer-based tricks. So one nice question to think about is like now that we know that this property is true, how can we use it to engineer an effect where, like we said earlier, if you have 10 cards, how can you ensure that, let's say, all the hearts pop out, like they're the only face-up cards at the end of it, knowing what you know about the property of this cut and flip operation. So so there's a question about what do I mean by a flip, like turn up to down or the other way and then swap positions. So actually the way you flip in hammer is basically you pull out like the top 4 cards and flip them flip them all at once, because that's what gives you, I think, this property, that when you have like a 0 1 state, you're back to a 0 1 state. If you flipped them individually, right, then that wouldn't quite work. So that would be a little bit different. So by flip, the operation itself is pull out the top 2k cards and then flip them over as a bunch and put it back. This is what it means. So actually, it's a nice exercise to confirm what Sunita is saying. So for instance, if you had like 4 cards in an arbitrary state, so let's say 0 1 1 1, for instance, and if you flip the whole thing around, um, does that uh, does that continue to respect the invariant? So I think it's a small argument, but an argument that can be made. Like here, for instance, if we take these 4 and we completely flip them, notice that the 1 2 will come on top. The 1 will come on top, 2 next, um, uh, then 10, and then 7. And also, instead of like white white, well, it'll still be white white black black is kind of the point, because the 1 2 would have come here and they would have flipped over, and the 7 10 and going down would have also flipped over. So hopefully that makes sense, that the pattern remains exactly the same when you flip things over. Okay, so I hope that sort of addresses that question about what do we mean by a flip. It's I think the thing to remember is that it's like a bulk flip. The whole thing flips over. Yeah. Okay, cool. All right, so we're well past the half an hour mark here. So I'm probably going to start wrapping up, but I do have like one kind of interesting question slash game that I want to leave you with. I'm going to try and see that this actually gets uploaded to the book reading website so that you can play with it in your own time. But here's like a really natural question that you can ask yourself. So given that you're only allowed to cut and flip, and let's say you're okay in the way that this is coded right now, it's hard coded to cut 2 cards, but in general, you can think about cutting any even number of cards. But the question is, if I only allow you to cut and flip, then can you achieve any desired target pattern? So for example, here I have this target arrangement at the bottom, which is this permutation 61 8 2 9 4 10 5 7. So that's the permutation. And like the cards 3 1 9 are face down, the others are face up. Okay, so basically, can I execute a sequence of hammer shuffles, a sequence of Kato operations, which leave me with this final target state? And I think it's a really nice question to think about. I will spoil this a little bit by saying that not all target states are achievable. There are some, there are quite a few that you actually can't. There's also like a really nice condition that you can come up with for staring at a target permutation and like immediately being able to figure out. So it's something that you can do. If you want to put it this way, it's something you can do in polynomial time. You can look at the target permutation and do some simple arithmetic to figure out if that target permutation is reachable by a sequence of cut and turnover operations or not. And you can also ask yourself how many of these permutations are reachable. And for the reachable ones, you can also ask yourself, like, what's the optimal number of operations to reach them? And I think this is a question that's probably not even fully resolved yet. So there's like a rich set of questions that you can ask here. And you can also ask yourself, like, giving yourself the power of cutting an arbitrary number of even cards from the top versus cutting only 2, is cutting only 2 restrictive, or can you simulate like cutting 4 cards with cutting 2 cards, for example? So that's also something that you can probably resolve. Okay. Uh, okay, so there is a suggestion in the chat which says all ups or downs need to be even. Um, so by Up and down. Okay, so your point is that all the face up cards and all the face down cards. Uh, I guess. Okay, I guess your point is that if you have a face up card at an odd position and a face up card at an even position, maybe that's not accessible. I'm not completely sure that that's true. It would be a nice, like, necessary condition if it were true, but I'm not sure that it is. So one thing that I think is fun to do is what I've been doing all day is to play around with a bunch of like cuts and flips and look at the kind of patterns that emerge to prove or disprove conjectures that you may have about what is the nature of the patterns that can be that can be pulled out. So here, for example, we do have face down cards at the first position and the 10th position, so odd and even. So it doesn't have to be that all face up cards or all face down cards share the same parity in the pattern. They, in terms of positions, they could be all over the place. Um, so I yeah. Um, So it turns out actually surprisingly that almost that any permutation is achievable provided you have the right face up face down pattern. So if you want a particular permutation, you can actually figure out what is like how the cards need to be in terms of their face up face down orientation for that permutation to be achievable through cut and turnover operations. So I think that's probably the last hint that I want to share on this front. I will confess that I'm also working through why the permutations that are reachable are reachable. If you are reading along and if you look at the book actually gives you the condition, but it doesn't tell you why it works. At least not unless I miss something. But I don't think it tells you why it works. So I think that's still like a really nice question. Okay, so there's clarification in the chat. So 4 cards are face up and 6 are face down. So they're both even, while in this target only 3 are face down, which will never happen. I see. I see. So you're saying, okay, so you were talking about the number of face up and face down cards being both even. I see. I don't know. Does anybody want to take a stab at that conjecture? Like the conjecture is that the number of face up and face down cards have to both be even. Yeah. Yeah. I think the number of, yeah, that follows from the invariant here, right? Because the total number of face up cards is the number of face up cards at odd positions plus the number of face up cards at even positions. So that's 2 times some number. So that's true. So that's a very good point. Yeah. Yeah. So in this case, I think, if I'm not wrong, this pattern is indeed impossible. So you were quite right about that. Thank you. Yes. But here you can see that there are some numbers which actually correspond to the condition that you can use to test, where I think the exact condition, which is a complete characterization. So the thing is, I think this is true. What you're saying about the total number of face-up cards have to be even is a necessary condition, but I think you can. It's probably not a sufficient condition, so you can come up with examples where this is true, but the pattern is not achievable, I think. So it so the final condition that's actually a characterization which says that this pattern is achievable by a sequence of by a hammer shuffle, if and only if the following is true. So that's, I think, a little more than the parity of the number of face-up cards. But I think that's a very nice point about, like, that's a quick sanity check that you can definitely do to rule out some patterns. Yeah. And I think the reason I'm kind of confident that it's not enough to just say that it's about the number of face-up cards being even is that I think the number of patterns where that is true, I think would be something like Yeah, n factorial times, I guess you choose, okay, so this is all bit strings with an even number of ones, right? Um, that's okay. What would that be? Whatever that is, that is more than the number that is already claimed in the book. So the number of reachable permutations turns out to be something like 2 times n factorial, and the number of patterns that have an even number of face-up cards would be much larger than that. Um, okay, so another condition is that if all the face-ups are at odd positions, that would also be impossible. Um, okay, so is that true? If all the face-ups are at odd positions, that would be impossible. So what you're saying is it's not possible to reach a state where all the even positions are face down, and maybe some others are also face down. But okay, so what's the reasoning? What's the reasoning for that? So let Okay, so the number of face-up cards at odd and even positions have to be equal. Right. So if all the face-ups are at odd positions, uh, oh, I see. Okay. If all face-ups have the same parity, okay. So except if nothing is face-up, I guess it would be which would be a silly thing to say, maybe. Like, yeah, if there are no face-up cards at all, then it's okay. But if there's at least one card that is face-up, then first of all, there have to be an even number of face-up cards. So we know that you can't have exactly one face-up card. And in general, if you have k face-up cards, they have to be split across the odd and even positions. So Sunita says it's back to the invariant. And yeah, and so does SSP. Okay, all right, thank you. Yeah, that's a good. Okay, so that's a good point. I think you can look at the target permutation and simply check if the invariant is violated. If the number of, like, you can say, well, if the number of face-up cards at even and odd positions are different, then this is not something that we can generate, at least from not starting from a permutation where the number of face-up cards at even and odd positions are equal. And here our starting permutation is a permutation where all cards are face-up. At least that's the context for this particular result. So from here, you cannot get to a permutation where there's a differential in the number of face-up cards in even and odd position. So you can definitely just check for the invariant. I think my point is that it's necessary for any achievable target position to satisfy the invariant. It's but you need I think you need to check for other things as well. So yeah, Sunita, it turns out that if I have the freedom to decide which cards are face up and which are face down, then every permutation is possible. Yes. So actually, maybe I can just go over what the condition is, what the characterization is for reachable permutations, because to be honest, I don't think it gives away much, because it's still not clear to me why the condition works. So if for those of you who really don't want spoilers, maybe disconnect audio for like the next 1 minute or so. But essentially, the condition is the following. Okay, so at every position of your pattern, you take the value of the card, you take the position, and you add up those two numbers, and you add a one if the card is face up, and add a zero otherwise. Okay, and then you write down all of these numbers as we have done here. And if all these numbers have the same parity, then the target arrangement is reachable, and otherwise it's not. So, in fact, the way this program generates these achievable targets is like this. It generates a random permutation and it flips a coin to decide if the first card should be face up or face down. So, for example, here, 9 is face down and it's at position 1. So, the value for position 1 happens to be a 10. So then you decide that forces the face up, face down configuration for the rest of the permutation because I know that 9 plus 1 is 10 is even. So now 6 at position 2 is an 8, so I should leave that face down. But 2 at position 3 gives me 5, so I should flip it face up to make that 5, 6. 5 at position 4 gives me 9, so I should flip that to make it 10, and so on and so forth. So basically, because if you believe that this condition characterizes all reachable patterns, then you know that every permutation actually can be achieved in exactly 2 ways. So you fix the you fix the face up, face down state of any card you like, and that forces the face up, face down state of the rest of the permutation. And yeah, so that's basically you have 2 degrees of freedom. So that's why it's 2 times n factorial. So yes, okay, all right, thanks, Ritu. So yeah, actually, maybe this is like not like this is a good place to probably pause and we can pick this up tomorrow. But yeah, so this is so if you click on this seems impossible, then you see these numbers which indicate whether the target permutation was achievable or not. So nice question again is to
Okay, found this on the web form.
oops.
Indicate whether the formation was achieved or not. Check it out.
Okay, I am so sorry. I think I said something that triggered. Okay, I don't want to say the trigger word again, but it triggered a friendly AI agent on one of my devices. So anyway, okay, so so this essentially is a characterization that tells us a few different things. It gives us exactly how many permutations are reachable. It gives us a way to test if a permutation is reachable. What it does not give us is an optimal way of reaching this target permutation. So that's something that's not like the algorithm for going from the base permutation to the target permutation. That's not completely clear. I'm also not completely sure if I give you an optimal if I give you an arbitrary starting pattern if there's some sort of an isomorphism that tells us that from any arbitrary starting pattern, again, there are exactly 2 to the n, 2 times n factorial patterns that are reachable. That's something that I was thinking about that was not clear to me. One remark in the book is that the set of achievable permutations forms, I think, a subgroup of the permutation group when the starting permutation is an identity permutation. So maybe that's of some interest. But yeah, so this I think was like leaned a little more into like the last part of our discussion leaned a little more into the math engine behind the tricks. But tomorrow when we begin, we will see how this engine can be used to rig some really nice effects. So we are going to see exposing all the hearts in a 10-card deck. I think we are going to see like a couple of other ways of using. We're also going to see how the 4-card trick works because if you notice when we start, this actually does not satisfy our invariant that the number of face-up cards at odd and even positions is the same. So this is a very specific rigging to make a very specific outcome happen. So why does this work is I think still an interesting question, even though we now have like some hints about what might be going on. Okay, so there are 2 questions in the chat which I will try to address. The last one first. Are the numbers in red related to what was the cut amount? And can we use the red numbers to determine what the cut amount is? Oh, here. No, unfortunately, this is no, the numbers in red are actually, it's just these sums. So the characterization says that at position I, sum I and the value at position I, the value of the permutation at position I, and add 1 if the card is face up and add 0 if it's face down. So the red numbers here are just like the sums of these 3 numbers. And the check is that if all the red numbers are odd or if all of them are even, then the pattern is achievable or it's reachable. And if not, then it's not. So that's all that this is saying, unfortunately. So maybe there is a way of reverse engineering like a sequence of cuts from these numbers. That's probably how they come about. But to be honest, I actually don't know how a proof of this characterization works. So I'm unable to comment on that at this point, but hopefully I'll have more to say in a future session after having thought about it some more. Okay, so Premanand's question is, can I show you how to do this with the tools given? Oh, as in, do you want to actually achieve this pattern using using cut and flip operations? Um, Actually, yeah. So in fact, one of the things is doing, but I couldn't finish doing, is I wanted to set up the same game, but with like 4 cards or something, because doing it with 10 cards, actually, even for the achievable one, seems like quite challenging because it seems like you have to anticipate quite a bit in terms of where the cards are eventually going to be, and the cuts, especially after the flips, really kind of mess around with the state. So I cannot think more than like 2 to 3 steps ahead, and it's, I mean, yeah, and since I don't have an algorithm, it's kind of it's a lot to keep track of manually. So, can we have a version with 4 cards by tomorrow? I'm working on that. Hopefully, we'll have a playable version with 4 cards tomorrow. For now, everything that I have so far should be up online like soon after this meeting. So I'll post an update in the WhatsApp group once you can go and play around with what is there right now. And once I have the version with 4 cards, I'll post another update. Yeah. Okay. All right, sounds good. Now we're actually close to even the hour, so maybe we call it a day here. Tomorrow we will try to understand why the 4 card trick works, and we will try to expose all hearts in a 10 card deck. And if we have any more understanding of this characterization, then we will discuss that as well. But yeah, this seems like as good a place as any to stop. If somebody has any quick feedback or comments, please feel free to chime in. But otherwise, we will all meet tomorrow anyway. Awesome. Thank you so much. All right, then. So we'll stop here and see you tomorrow evening. Bye-bye.